See if we can get a screen up here. Working on it, all right. All right. Are we working? Yes, we're working. Okay. So Pau asked me if I might say some things about some recent work that has been going on at Penn State on gravitational wave bursts from extreme mass ratio encounters. And so there are a couple of things here that I want to, just before getting started on, draw your attention to. One is we're talking about something that is very similar to what we talk about in terms of the source characteristics. That is, we have a central supermassive black hole or massive black hole, and we have a stellar mass object, and we have a close encounter. The difference is that where an EMR is an in-spiral event, that is where the radiation is predominantly in the Lisa band, and it lasts for on order a year, and we see perhaps the merger. Here what we're talking about is something where we have a, the energy is not predominantly, or excuse me, the energy may be predominantly in the Lisa band, but in fact the orbital period may be much, much longer than the time scale for the Lisa band. The orbital frequency may be much, much less than 10 to the minus 5 hertz. Yet there still can be a significant signal from these sources. And so there really are burst sources here. So let me just talk a little bit about these sources. So stars enter the loss cone associated with a supermassive black hole with very large eccentricities. And so they enter essentially on nearly radial orbits from a very large distance out in the nuclear cluster or the galactic bulge, or as Cole and Melvin and Mark have described, they may be a binary that was injected from a very large orbit, but owing to a tidal disruption, the star really entered into an orbit about the supermassive black hole at still a smaller radii, but nevertheless still with large eccentricity, just not quite as large. The periapsis passage of that star can take place with velocities very close to the speed of light, leading to a gravitational Bremsstrahlung event. And so the time of peripassage, or the time scale for the peripassage, would be the velocity divided by basically 2 pi times the impact parameter, or the radius of the peripassage. So you'll get a burst of radiation at this frequency. This frequency can be within the Lisa band, while the orbital frequency can be, in fact, very much outside of the Lisa band. So you'll have a burst of radiation, perhaps. Now, there are a couple of things that go perhaps, I mean, it's more than numerology, but less than precise. But still, I think it's very important to recognize this also holds true for the typical EMRs and IMRs that we talk about as well, and it has implications that I want to come back to. Let's ask the question, what is the ratio of the strain from the gravitational waves at periapsis to the strain at apoapsis? Okay, so now I'm talking about EMRs, I'm talking about these extreme mass ratio encounters. Let's just say Kepler, then h peri over h apo is basically the second time derivative of the quadrupole moment at periapsis to the second derivative of the quadrupole moment at apoapsis. That's the kinetic energy at periapsis to the kinetic energy at apoapsis. And that's 1 plus e over 1 minus e. For large E, that can be a very large number. And I've plotted it up here, what that ratio can be. So for a 0.99 eccentricity, you're talking about a ratio in the strains of 10 to the 4. For 999, you're talking about 10 to the 5. That's a significant difference in the strains, and that means quite a bit for I think the data analysis problem. I'll come to that in a little bit. The other question that we can ask, which is a very relevant question, is kind of what's the duty cycle? In particular, when we're talking about ratios of strains that are so great, we might want to say, well, it's basically an on-off process. And we can ask, how long is the burst on for? How long is the signal from the in-spiral there to the orbital period? So we can talk about the duty cycle, the time spent at periapsis to the total orbital period. Again, from Kepler, that's a relatively straightforward calculation to do. And in fact, we find, again, that for large eccentricities, the duty cycle is quite small. So again, for 0.99, we're talking about significant radiation in terms of strain for only a part in 10 to the 3 of the total period. And it gets obviously even smaller as you go to larger and larger eccentricities. Obviously, when you talk about IMRIs, which have eccentricities when the signal is entirely in the LISA band of 0.998, you have a very strong pulse for a very short period of time, and then, relatively speaking, nothing. So now let's kind of do these numbers in a little bit more detail, and we'll use the results from Clovis and Tal. If we talk about their scenario, where they give results from, they talk about the situation where you have an in-spiral, about a 3 by 10 to the 6 solar mass black hole, and the orbital period now is about 10 to the minus, I can't now remember, what did you guys use? 10 to the 4 seconds. Okay, so the signal is entirely within the LISA band here. So it's what you would classically call an EMRI or an IMRI. Okay, the ratio for EMRI sources, where the peak eccentricity is around 0.7, peri to apo is a factor of 30, and the duty cycle is only 12%. For IMRI sources, peri to apo is a factor of 1,000,000, and the duty cycle is just a little bit over a part in 10 to the 5. So the situation here is that if we think about the signal to noise, and again, I'm going to come back to this point. If we think about the signal to noise is almost entirely deposited in this case, 10% of the observation time, and in this case, a part in 10 to the 5 of the observation time. Yeah.
Just one clarification. It is an EMRI, but it says that it's stellar mass object or it's an intermediate mass spectral.
I'm sorry. Yeah.
EMRI,
yeah. That's right. Yeah. No, I misspoke. Thank you. I'm glad you corrected me. So the signal to noise is deposited over a very small fraction of the orbit here. Caveats to keep in mind as we talk about these kind of numbers is that Kepler's not quite right when V is on order C, and that will lead to some changes here. It'll change things quantitatively, but not qualitatively. And the other thing is that when we're talking about burst sources here, the more relevant eccentricities that we should be focusing on are the eccentricities when the peripassage time is inside the Lisa band. The period could be well outside the Lisa band. And in fact, because these guys, this samples a much larger amount of phase space where things are evolving more slowly. In fact, there could be significantly more objects here than your classic in-spirals, EMRIs or IMRIs. So now what Louis Rubo, Kelly Holly Bockelman, and I did was we took a look and we said, well, if there are going to be, if we're sampling a larger region of phase space and we have many more objects, then it may be possible that we have bursts where each individual burst may be detectable, coming from much closer to us than what we think of when we think of an EMRI or an IMRI. And so what we did was we took a look at the galaxy and the galactic neighborhood out to Virgo, and we modeled the galaxy as an Eta model with an embedded black hole, typical of our galactic bulge and typical of the black hole in the center of our galaxy, 3 by 10 to the 6 solar masses. We took a Krupa initial mass function for the stars in the bulge. We also explored a Scalo and a saltpeter IMF, and it didn't make a whole lot of difference in the final results. We found first the phase space fraction that led to bursts in band. So that was this V peri over R peri on the order of 10 to the minus 3 hertz. We excluded plunges that would just give, kind of one quick burst that really didn't follow this pattern here. And then we asked how many of these bursts from the galactic center would have a signal-to-noise ratio greater than 5. And what we found was from the galactic center that we would expect approximately 12 per year, 12 bursts per year, not 12 objects per year, but 12 bursts per year with a signal-to-noise ratio greater than 5. And these were mostly things that would not be, you would never see as EMRIs, low-mass main sequence stars. Yes? That is in one burst. Absolutely. Well, you're not going to see it in a 3-week average. What you're going to see is you're going to see a burst of radiation whose time scale is essentially the time scale of the peripassage, 10 to the 3, 10 to the 4 seconds. No. No, these are strictly time domain bursts. And then if we go out to the Virgo cluster, in fact, there are 3 per year that one can expect from there. These, on the other hand, are all about 10 solar mass black hole into 10 to the 6 solar mass black hole type of objects. Over here on the right, what vindicated here is basically the number, if you will, of objects, a relative number of objects versus the log of the signal-to-noise ratio. Everything in the grayed area are things that at the galactic center have a signal-to-noise greater than 5. Some, you'll notice, have signal-to-noise greater than 10 to the 4. These are the ones that we would see from Virgo. The other thing to note is in this particular model, the orbital period. We looked at the orbital period of these guys that were giving observable bursts. The orbital periods were, half of them were greater than 4 days, half of them were less than 4 days. So they're principally outside of the LISA band, but they're giving, for each burst gives an observable signal. And so when I say, for example, 12 per year, half of those are on 4-day, or half of those bursts. Now let's start that again. 12 per year. Some of those are from objects that are on 4-day period orbits, and so, you know, for that fraction, you would see a significantly higher number if you found some things there. So this gives a distribution for here. So now let's do a little bit of talk about some of the implications here, some of the limitations of the work. So one of the things that we did, which is a limitation, is that we treated the bulge as spherical. In fact, our galaxy likely has a bar. It certainly is triaxial. So there are going to be centrophilic orbits, and centrophilic orbits can increase the rate by up to 2 orders of magnitude. On the other hand, and the median P orbital would be larger than in the spherical case. So it would change things in this way. On the other hand, we did not treat mass segregation here. And if we incorporate mass segregation, that could decrease the rate of bursts, particularly from the low mass main sequence stars, by about 2 orders of magnitude. So there are a couple of significant places for further investigation here. Finally, we treated the radiation and the orbits, basically the orbits as Kepler, and the radiation as quadrupole approximation. Since V Peri is on order C, we have to be worried about higher moments radiatively, and we have to be worried about beaming in these orbits. So these are places for investigation. This would give us some selection effects that are important. Now, coming back to something that I stressed before, most of the signal to noise is deposited in the peripassage burst, and that's also true for EMRIs and IMRIs, except at the very end of an EMRI or an IMRI, we really don't have a continuous wave signal. We have something that looks much, much more like a train of bursts of short duration and larger gaps. So this has implications for data analysis. Do we need waveforms outside of the peripassage? And can we model the waveforms during the peripassage in a much simpler way? A lot of effort goes into computing waveforms, and a lot of that effort may be spent in computing parts of the waveforms which contribute very little in the way of the total signal to noise. Now, if we do that, well, in any event, we end up needing to match up nearly periodic bursts. The period of the bursts, the interval between the bursts is going to be decreasing with time owing to radiation reaction. And that leads us to the next point. The orbital evolution of these guys is, and Kurt has made this point over and over again, the periapsis doesn't change much. The apoapsis grinds its way down with each orbit. The self-force is active principally during peripassage when the signal to noise is being deposited. That is mostly when things are going on. So it is during the period when the signal is strongest that almost all of the orbital evolution is taking place. And that's problematic for computing the waveforms in the region where we need them the most. So the self-force calculations are perhaps even more important than we may have originally thought. Matched filtering requires that we get the orbital evolution right in this sector. So we have to have the self-force calculations sufficiently accurate that over that very short period of time, when almost all of the orbital evolution is taking place, we get things right. The other thing, of course, is that successive bursts are going to be different because there will have been considerable orbital evolution in that interval. So just in conclusions, what we found is that gravitational wave bursts, each burst with a significant signal to noise, are generated by extreme mass ratio encounters in the galactic center and in the Virgo cluster, and it may add up to tens per year of bursts visible in LISA. It's possible that the rate is a diagnostic. For these bursts, we're talking about things that we know are the galactic center, or we know are Virgo. For these bursts, then, that may give us something of a diagnostic for the triaxiality of the bulge, and it may give us convolved in some sense with mass segregation there. The ratio of peri to apo, and this is true for both these bursts, but also for EMRIs and IMRIs. Peri to apo ratio in strain is very large, and the duty cycle is very small for small 1 minus eccentricity, for large eccentricities. And this has really significant implications, I believe, for how we approach the data analysis for these and the degree of accuracy we need in the self-force calculations as well. In particular, we can throw out, if you will, everything that happens between peri passages, recover almost the entire signal-to-noise ratio, do basically as well as if we had matched filtered the entire waveform by focusing only on the radiation and the waveform at peri passage. Thank you very much. And Kurt. Mark and Kelly and Lewis and I were in close contact throughout the entire affair. And Mark, in fact, Mark's work was very important for informing our understanding of the mass segregation, which we ignored. And so yes, I mean, there's quite a bit there.
What I completed was different.
Yeah.
It was EMRI in the sense that the whole period was the orbital period was limited. Yeah, still million years in the band because they were very low mass stars, significant stars. They would evolve slowly and you can only detect them if they are very close. Okay, cool.
So basically, mass segregation might drop your low mass rate a lot because it's your low mass, and therefore
Mm-hmm.
that would increase the rate of Virgo cluster because of the low mass size.
It certainly would increase the relative rate from the Virgo cluster. That is, the rate of Virgo cluster. For the Virgo cluster, all we did was we scaled the Milky Way to the distance and multiplied by the number of galaxies. It is only the very massive objects that give sufficient signal, that radiate sufficient energy, such that the signal to noise here from the Virgo cluster is enough to see. And those turn out to be the 10 solar mass black holes. So it would certainly, mass segregation would increase the relative number of sources from the Virgo cluster compared to the low mass main sequence contribution from the Milky Way. I'm not sure how all of the different effects would play out.
I had a question about
Right.
so what days or so during the period long enough for the change in momentum, therefore
Yeah, it is certainly possible. We only excluded the direct plunges. We didn't track these orbits beyond that. No, those 12 bursts per year. And so in some case, those are objects that are on long period orbits, but period orbits that might be a year or less. Mm-hmm. That's right, but that's again that's part of a probability distribution. So you have to ask the question, what do you have? What I didn't give you there is if we were to do many different instances, what would be the variance in that rate? The variance would be high in that case. Yeah. Right. No, that's a good question, and I feel very chagrined that I hadn't thought of that issue. You'll have more of them. What I don't know, the duty cycle is still small, so what I don't know is whether or not we're talking even popcorn noise, or if we really have a stochastic, a Gaussian background. Do we have enough? I don't know the answer to that, but that's a really good question.